Today's, I know, I'm a realist. Please notice the title of this section is called Average Value of a Function. Now, there is one thing that is needed in this lesson that Sparks does not teach you. So I'm going to teach that, and what I want you to do is take your notes for this on the back, because I think the back of this is blank. The fundamental theorem of calculus really has two parts. You've already learned the first part. The first part says the integral from a to b of f prime of x dx equals f of b minus f of a. That is one part of the fundamental theorem of calculus. Now, there is another part that is used in this lesson, but Sparks never addresses it. Okay. Now, I wrote my notes, so let me get my notes as to exactly how I want to do this. Okay. This is going to look just ugly. That's what you're getting ready to learn how to do. What in the world is that? This says the derivative with respect to x of the integral from a constant to x of f of t dt. I'm glad you mentioned that. In certain cases, the derivative and the integral are inverses, and they will cancel each other out. Now, what you have to know is what cases. Now, I want you to write this down. We're actually going to do one. We're going to take the derivative of the integral from 3 to x of t plus 2, oops, put that in the wrong place, dt. Carson, you better be learning this, buddy. I have faith in you, Carson. So does Evan.
I second.
Okay, Drew seconds. Okay. You know how to do that. You know how to take the integral of t plus 2. What's the antiderivative of t plus 2? Half t squared plus 2t. Yeah. So we're just going to write this part down again. So that's going to be 1/2 t squared plus 2t evaluated from 3 to x. Now again, we're going to ignore the d dx. We're going to ignore the derivative part, and we're going to actually finish that integral. So we're going to evaluate this at x minus evaluate it at 3. So what's that give us? 1/2 x squared plus 2x minus, what's that? 1/2 of 9, right? So 9/2 plus 6. So I've got to subtract that. What's 9/2 plus 6? Good. Do you understand where everything came from? We did the integral part. Now, notice that these variables match. This is x. These are x. I can take the derivative with respect to x of this polynomial right here. Take the derivative. What do you get? Where'd this go? The derivative of a constant is 0. Now I want you to look here. X plus 2. And I want you to look here. What the? Huh, we just changed the variable. Ladies and gentlemen, A derivative and an integral are inverses when you're integrating from a constant to some variable, and that variable match. So you can take the derivative later. So again, a derivative and an integral are inverses when you are integrating from a constant to some variable, and these variables match. Then you have inverses. From a constant to a variable.
Oh, I see.
When that happens, your answer is going to be this expression evaluated right here, x plus 2. That is the second part of the fundamental theorem. What do you think the answer to this is? F of t. This is f of t. Now I'm going to throw one little spin on this. We're going to use the same integrand, meaning we're going to integrate the same thing, but we're going to do it from 3, and it doesn't have to be 3, it can be whatever I want, 1 to x squared of t plus 2 dt. Now before we start, we're going to do this the long way, just like we did the last one. What do you think the answer might be? X squared plus x squared plus 2? X squared plus 4? Let's see. Let's do the integral. So we're going to do this part. Derivative with respect to x of. Now that's 1/2 t squared plus 2t evaluated from 1 to x squared. Okay, so what do we get when we evaluate that expression at x squared? I'm going to substitute everywhere I see a t. What am I going to put in its place? X squared. So I put an x squared in here for t. What's that going to become? X to the 4th. So that's going to become, yes, plus what am I substituting in here for t? X squared. So help me out. 2x squared. Yep. Now, these variables match, so we can take the derivative. What's the derivative? (2x cubed plus 4x. Can I go up? Yep. How far? What did I do? Oh, yeah. Because I'm an idiot. I forgot it. Minus what? 1/2 plus 2? 5/2? No, I forgot it. Is the derivative still the same? Okay. I was thinking ahead of what I wanted to do next, and I forgot the constant. My bad. There you go. Now, that's not what we thought. Hmm. Hmm. Sometimes you just got to accept surprises. What's the GCF? Times what? There's the x squared plus 2 we thought we'd get, right? We thought that this would be x squared plus 2. But it's x squared plus 2 times something else, times 2x. Where do you think that? That's the derivative of x squared. Right. Right. The second part of the fundamental theorem says it's this evaluated here, so x squared plus 2 times the derivative of this. Now, why did we not have the derivative of that on the last one? Because the derivative was 1. Yep. Yep. Isn't that cool? I think that's pretty cool. Now, that's required in this lesson, but he doesn't explain it. And I'm like, how do you not explain that? So, that is that. I don't know what he assumes, but no. Now, he does. He does require us to make assumptions. I still like his curriculum, so that's why I keep using it, because it's still the best I've used. Now, can I write a general rule? The derivative with respect to x of the integral from a constant to f of x. Now, this is good. Maybe I don't want to use f. G of x. Let me see if I like that. Yeah, that'll work. This is C. I don't know why that looks like a 0. That's it. Remember, a derivative and an integral undo each other when the integral, the limits of the integral are going from a constant to some variable, and this variable matches this variable. Yeah. So what are you going to get when you do this? You're going to get this function evaluated at, you're going to get that function evaluated at that upper limit times the derivative of that upper limit. Okay. Now we got one other thing we got to talk about. Oh, mercy. Now listen to me. If we don't finish, and I'm not sure we will, during last period today, I will do another video. Where's the rest of my thing? And I will post both videos, okay? And you're going to have to watch it. Yeah, I'll have to see how far I got. Because that's right, I could do that. Where's the rest of my, where'd it go? There it is. I'm not doing that right, am I? Okay. Average value of a function. Do you remember how we have found average velocity before? And how'd we do it? That's right. That's right. So average velocity is the change in position divided by the change in time. if we find average velocity by the change in position divided by the change in time, how do we find average acceleration?
Change in velocity.
There you go. Change in velocity divided by change in time. So V of B minus V of A over B minus A. So that's going to be the change in velocity divided by the change in time. Now, this piece is the other piece that I've got to just flat out teach you. And if you want to write this down, fine. If you don't, it's not a big deal. If you want to just really focus and pay attention to what I'm doing. I'm going to draw a little diagram. I'm put a little graph. And that's f of x. Now, I'm wanting to find, dummy, that ain't gonna work, is it? If I integrate from a to b of a function whose graph I am given, what do I find? There you go. I'm finding the area under that curve bounded by those two vertical lines and the x-axis. Yes? So, what I'm finding is this area. Now, I contend that there is a rectangle whose width is the distance between A and B. There is a rectangle somewhere in there whose height, let me say this, the x value is c. What would the height be? What would that point there be? C, comma, f of c. I would contend to you that there is a rectangle in there somewhere whose area is the same as the area under that curve. Heck yeah. Heck yeah. You might be able to kind of envision it, even though this is freehand. Can you kind of envision that this little piece and this little piece are kind of similar? Okay. So, I'm going to take that out because I don't want that to confuse you any. But there is some rectangle whose area is the same as the area under that curve. Now what I want to do is I want to find the area of that rectangle. Now you think about that for a minute because I got to help Maylin for a second. How do you find the area of a rectangle? Base times height. What is the base of that rectangle? AB, B minus A. B minus A is the base of that rectangle. What's the height of that rectangle? F of C. The area of that rectangle is F of C times B minus A. Its height times its width. Yes? But what I know is that F of C times B minus A is equal to the integral from A to B of f of x dx. You buy that? You buy that? Now, I want to get f of c all by itself. How can I do that? Good. And dividing by b minus a is the same as multiplying by 1 over b minus a. That is what we call the average height of that rectangle. That's the average height. The average height equals 1 over b minus a times that integral. Ladies and gentlemen, this is the equation for average value. And to do that swimming pool problem on the ACTM? Right there. Right there. Okay. Have you written down anything you want to write down? I hope I haven't been. Have I been recording? I hope I didn't miss anything. I'll scroll down just a second. That height of that rectangle is what we call the average value. And it'll roll off your tongue. It's 1 over b minus a times the integral from a to b of f of x dx. It'll roll off your tongue. Okay, you got it? Now let's go to your notes. Okay, so I want you to take a look at this. If P of t, V of t, and A of t represent position, velocity, and acceleration, write an equivalent expression for each of the following integrals based on the fundamental theorem of calculus. Now, the fundamental theorem of calculus says this right here is equal to what? When you integrate acceleration, you get velocity. So the part that I've circled or squared up in green is V of B minus V of A. Okay? Multiplying by 1 over B minus A is the same as dividing by B minus A. Holy smoke. That is average acceleration. Good, good. If your brain doesn't hurt when you walk out of here, I am sorry. I will try again next time.
I think I passed I just got to the point where my brain goes into this trance mode where literally nothing makes sense. I'm just like, all right, I'll write it down. I'm just like, probably.
Are you just in the zone?
Writing it down. No, it's not even like I'm in the zone.
Not even in a zone.
So out of the zone that it just
So out of the zone. All right. So look, average acceleration. You are integrating the acceleration and dividing by B minus A. Now what about this one? What's this piece using the fundamental theorem? Good. P of B minus P of A. But then we pull this part in, so that's over B minus A. What's that? That's the average velocity. Okay, mind blown. So, the average value of a function f of x on an interval a to b is defined to be, what do you think it is? How could we write it formally? Average value, 1 over b minus a times the integral from a to b of f of x dx. Now, find the average value of this function on the interval 1 to 3. Now, before you do it, I want you to write down right here what you're going to put in your calculator. Average value, let's use that formula you just put in the box. It's going to be 1 over what? 3 minus 1, so 1/2 of the integral from 1 to 3 of that function. Now, please, that's x cubed. That is not a cube root. That's x cubed. Make sure you remember how to put signs squared in the calculator. It's like that. Run this on a blank screen. Sparks got 5.848. Now let's move on. You can come back to that one, Gisela, but now you know what you're doing there. Okay, this is a non-calc. Now what we're going to do is we're just going to set it up and we're going to move on, okay? How do we write the equation to find the average value of this function on this interval? 1 over 6 minus 2, which is 4, times the integral from 2 to 6 of 2 minus 4x dx. You guys can all do that integral. No issues there. You should get on that one, I'll just put over here, you should get negative 14. Now we're going to get to the good stuff. A ski resort uses a snow machine to control the snow level on a ski slope. Do you know they do that, right? Over a 24-hour period, the volume of snow added to the slope per hour is modeled by this function S of t. Volume added. Now, is that a rate? Because it's per hour. The rate at which the snow melts is modeled by the equation m of t. Both S of t and m of t have units of cubic yards per hour, and t is measured from 0 to 24, so that's a 24-hour period. At time 0, the slope holds 50 cubic yards of snow. Please, please, do something, highlight it, write 050, something, so that you don't forget that piece. No, it's not 50 for either of them. It's just, it has nothing to do with S or with M. It's just at time 0, there's this much. When they started measuring, there was this much snow. Initial condition. Look at A. Compute the total volume of snow added to the mountain over the first 6-hour period. Now think about what you got to do here. Am I going to use S of t, or am I going to use M of t, or am I going to use both? Just S of t, because I want to know how much was added. Do I care about the 50 cubic feet that was there, or cubic yards that was there when I started? In question A, all I want to know is how much was added those first 6 hours. That's it. That's it. So what are we going to integrate? We're going to integrate S of t dt from where to where? 0 to 6. Here's what I want you to do. I want you to put S of t in y1. I want you to put M of t in y2, because we will use them more than once. Spark says 142.413. Anybody? I got a yes. I think I know what's going on. When you type this into your calculator, let me look at it. Well, snap. Okay. You type it in like this, 24 minus t times sine of, well, that's going to be x, right? That's how you type it in. I think that's what's messing with you. What unit? This is volume. Cubic yards. Dang it! Stenett's going to getting ready to bust a gasket here in a minute. Why is it? Okay, there we go. Dang it! There. Cubic yards. Okay. Dadgummit. Now let's look at these two. We need to find both of these values. Now you should have M of t in your Y2, yes? Okay, I want you to run this, and I want you to run this.
It's not like a karate.
I like the fact that
Run those two real quick. I'll write down what Sparks has. Sparks gets 81.823 and 13.637. What does the integral from 0 to 6 of m of t dt mean? What's it mean? Look at what m of t meant in the first place. Remember, m of t was the rate at which the snow melted. When you integrate a rate, you get an amount. So what does this tell us? That's right. And what unit? Cubic yards. So this tells us that this many cubic yards of snow melted during the first 6 hours. What does the second tell us? The second number. That's right. During the first 6 hours, the average of snow that melted per hour was 13 point something cubic yards. The last one, during the first 6 hours, the average amount of snow that melted per hour was this many cubic yards. Or you could say the snow melted at a rate of this many cubic yards per hour. Now we have got to get through this piece right here. Got to. Is the volume of snow increasing or decreasing at time t equal 4? How do you determine if something is increasing or decreasing? You take its what? Derivative and do what with it? You see if the derivative is positive or negative. Right. So what we've got to do is we've got to have an equation for the volume of the snow. We got to write an equation for the dang volume of the snow at any time t. Somebody was looking in the window. Notice this says at time t equal 4. But I'm not being asked how much snow is there at time t equal 4. I'm being asked, is the volume increasing or decreasing at time t equal 4? So what I got to do is I got to write an equation for the volume of snow on the ground at any time t. I got to use them both. What do I do with the integral of s and the integral of m? I will subtract them. But what are you forgetting? The 50. The amount of snow, the volume of snow on the ground at any time t is going to be what was there when you started, plus, now I'm going to do this funny and you're going to wonder, but I'm doing it anyway. And I'm going to put my limits in a minute. I add the snow that was added, and I subtract the snow that was melted. With me? Now, the snow started being added and started melting at time 0. I want to know the volume of snow at any time t. So I've got to integrate from 0 to t. This variable and this variable have to match. But this variable and this variable cannot be the same variable. This x, this is a dummy variable. Doesn't mean it's stupid. It means I can use any variable I want. I just cannot use t. I can use anything. Now, to determine if the volume is increasing or decreasing, what do I do with that formula? Because this is a formula for amount. Take the derivative. How do I take the derivative of an integral? Oh my gosh, I just learned how to do that because that's the second part of the fundamental theorem of calculus, right? So, v prime of t. What's the derivative of 50? 0. Now, look at this piece. I'm taking the derivative of that with respect to t because that's the variable I got over here. And that's the variable I got right here. So what is the derivative of this integral? It's s of t minus the derivative with respect to t, m of t. I don't have a chain rule because we went through all that, remember at the beginning? No, times the derivative of that, which is 1. Now, on your calculator, we want to find v prime at 4. So we need to find v prime at 4. So can't you just do y1 of 4 minus y2 of 4? Don't you have those in y1 and y2? Okay, run them. What are you getting here? Good. Now remember, this is still for part C, not for part D. V prime of 4 is 11.8. Look at the question. Is the volume of snow increasing or decreasing at time 4? Why is the volume increasing? Because the derivative is positive. Perfect. So all you have to say there is the volume of snow is increasing at 4 hours because V prime of 4 is positive. Now we got 2 more parts to look at. Ah, snap. That's another snap. Come on. How much snow is on the slope after 5 hours? What are we going to do? How much snow is on the slope after 5 hours? That's right. Ava says we're going to evaluate V of t for 5. Because wasn't this a formula for the volume of snow on the slope at any given time? So let's just do this. Golly bum. So the volume at 5 is going to be the 50 plus the integral from 0 to 5 of s of t dt minus the integral from 0 to 5 of m of t dt. Don't take the time to solve that. 95.335. 95.335. That's what Sparks gets. But what's the unit going to be? Good, cubic yards. Now look at this one. We get through this one and we'll be fine. Suppose the snow machine is turned off at 10 hours. Write, but do not solve. Now, you will see this now and then. Don't solve it. Just write the equation. Don't solve it. An equation that could be solved to find the time t equal k when all the snow's going to be melted. What do I have to know? Say again? I'm definitely going to have to use m of t for sure. Set what equals? Why would I set something equal to 0? So what do I want to equal 0? I want v of, I want v of, essentially I want v of t to equal 0, right? Well, let's think about this. Can we figure out how much snow there is at time t that we're going to have to melt? How much snow is going to be on the mountain? Remember, we're right here. How do we figure out how much snow there is on the slope? Say again? Yeah. You're going to calculate this, aren't you? You got to figure out how much snow there is. So we're going to find v of t. V of 10. So that's going to be your, what, 50 plus the integral from 0 to 10 of s of t dt minus the integral from 0 to 10 of m of t dt. Yeah, I'm not going to be taking a derivative. See, do you see up here my upper limit is a constant? If my upper limit was going to be a variable, then I'd have to switch them. But because my upper limit is not a variable, I don't have to worry about it. Now this gives you, I'm just going to write down the number. This gives you 183.193. How much snow is on the slope after 10 hours? That much. How much snow has to melt? That much. What are we going to do? What are we going to do with m of t? That's right. I want m of t to equal this. I want m of t to equal, now do I want m of t to equal this, or do I want the integral with m of t to equal this? Because m of t was a rate, wasn't it? Snap. M of t was a rate. So to find the amount, I'm going to have to integrate. So I want the integral from where to where of m of t dt to equal 183.193. From where to where? Why do I start at 10? Good, good, because that's where we're starting. That's when we have this much snow on the ground, and it's going to go 10 to where? Okay. That is the right, but do not solve. You did it. Now the last piece on here is a free response. You need to do that free response. I will post, now this is my handwriting. I worked the problem myself. I'll post that, and I'll give you your assignment.
Wow.
Whoo! No. Now.